Good morning. Okay, I actually thought that I was a programming expert in APL, but I think that expired 20 or 30 years ago. How's the light situation? Are the colors okay for the lights on? We can do it this way. Okay, so the explanation of the title of this talk is that the whole thing would be rather a long talk, and today we're going to be basically limited to part 1 of 3. So I hope that won't be a disappointment for you. We'll do DNA, a little bit of APL, and I spoke at an APL conference about, it must be 15 years ago in San Antonio. Ken Iverson was there, I remember, and talked about my DNA work. And I gave a talk somewhat like this 2 or 3 years ago in Florida. So in giving this one, first thing I had to decide was whether I should give the same talk or a different one. I think last time I included maybe 5% of APL, but I think that was probably more than enough, so I might cut that back. The second question is whether to use the same jokes. And I was reminded of a remark of my uncle, my namesake, Uncle Charles Brenner, most honorable man, before he became seriously ill, who he made this remark about his brother, my father. And so I thought maybe that's good advice. So in order not to let good jokes die, I'm going to use them again and again, if that's all right. Okay. All right. Another point. I thought it's usually a good idea to check at the beginning of a talk if you can hear me clearly in the back. You can. Some of you can. Okay, that's good, because the problem is a few months ago I gave a talk in Philadelphia, and I was halfway through the talk, and I said, "Can you hear me in the back?" And a lot of the people in the back indicated they couldn't hear, and at that point, the entire front row got up and moved to the back. So it's really a lot better to do that at the beginning. Here's my background. I graduated from college originally in '67, and then stopped by T.J. Watson Research Center, where I was following my friend from college, Larry, and I worked a bit on APL development at that time. Then after some years in England, where despite my plan I didn't get a Ph.D., dropped out of college and did other dissolute things. I came back, worked for an APL company that most of you remember, STSC, and then a few other little thises and that's for the last health, doing an application, which is the basis of this talk. My childhood interest in mathematics, very pure mathematics. And in fact, if anything was applicable in any way, it seemed to me that it was thereby tainted. So it's a little surprising to find the kind of mathematics that I'm doing. But in a way, I learned applied mathematics when I was trying to make a meager living playing bridge down and out in London some years ago. And what I'm doing now I call forensic statistics, which I'll explain in a Well, it has some red lights. Okay, no, it's doing something. It's fine, but it's a question of if I throw the tie over my head, that would have some pluses and some minuses. I'm going to try moving this up a little bit. Actually, I don't mind holding. If I look down like this. Okay. Anyway, what actually happened was that I worked less hard and made about the same money. And soon, for various reasons that I needn't go into, I decided to go to graduate school, which was a very enjoyable experience. I was a little better equipped for actually studying than I had been when I was younger. And I learned some of these weird mysteries that I'd known about all my life in mathematics, like why you can't solve a quintic. And eventually I got a Ph.D., which amounts to a credential in the work I'm doing now. I don't actually use advanced mathematics. I use multiplication a lot and a certain amount of long division. And I'll show you some of that. I'll show you my super simplified version of Bayes' theorem. In 1982, among my various consulting gigs, I came upon one with an old friend from college who was running a paternity lab that led to learning about genetics. And I never looked back. It was a matter of joining my mathematical interest with software interest. And it was much more interesting for me than learning about how you handle third-party insurance claims. So I was able to clean out a small corner of my mind that had that particular knowledge based on something I did in Bakersfield. It's shameful. I don't want to talk about it. So I had to make a name for my software, and the name is DNA View. And now I'm used to it. It's about DNA, and I guess there were various pieces of software called DNA something. That was probably the inspiration, which was not a very good one. I'm very bad with proper nouns. However, after the years, this has become well respected in the world of DNA identification, which is a narrow world. And I've also had the enjoyment of working with a lot of scientists, including World Trade Center identifications, identifications in the Balkans for the war in the 90s, and a lot of other mass disasters. This is actually more or less an offshoot of a feature of the software which I call kinship analysis, which I'm going to talk about a bit in this talk. Generalization of paternity, which includes problems like missing body identification based on relatives, comparison with relatives, inheritance questions. You know, these kids are written into the will, and this kid says, by the way, I'm almost sure that that rich guy had an affair with my mommy, and I'm a half-sibling of these people. Let's get some DNA and prove it. So you need some way of analyzing the DNA to say, are they half-siblings? Twin zygosity means, are they identical or fraternal twins? Nobody really knew until there was DNA identification. And another advanced application, see, the simple application is when you have a DNA profile at the crime scene and you have a suspect and they match exactly. The calculation is fairly straightforward in that case. Well, don't laugh. There is a calculation. I know in fingerprints they match exactly. It means it's the same person. Proof positive. And they often say to us in various contexts, like lawyers say to the DNA experts, why doesn't DNA work like fingerprints? You know, you guys come into court and you give these numbers like 10 to the 15. In effect, they're saying, why can't you just say infinity, damn it? Between 10 to the 15 and infinity, is there really a big difference? No, there's not. But what they're saying to us is, what I say is, oh, you mean you want us to do DNA like the fingerprint people claim fingerprinting works? You want us to you want us to tell the same lies they're telling? Well, there would probably be less lies in our case. And finally, okay, yeah, I better turn. That reminds me, I have a mute on here. So if there were any sound effects in this talk, we would have missed them. Now we're okay. And why chromosomes? Well, it's another really fascinating area. because the genetics of the Y chromosome are different in wonderful ways from the other chromosomes. We'll take a look at the chromosomes in a minute. Forensic mathematics is the mathematics of DNA identification. Why, you may ask, specifically DNA? Why can't you have forensic mathematics covering forensic accounting and fabrics and broken glass? And I'll tell you why. Because until I thought of it, there was no term forensic mathematics. I couldn't very well call myself a forensic statistician because someday I might run into a real statistician and I'd be exposed as a fraud. Because I never studied statistics. And on the other hand, no actual mathematician had ever sullied himself by going into such an applied area. So the term was free for me to grab and use. And as you probably know, if you're the person who invents a term, you're allowed to define the parameters of it. So the fundamental concept of forensic mathematics is whatever I say, and so on. Anyway, it deals with paternity and the generalization of paternity as kinship, which I mentioned in a previous slide. It deals with crime, and the simplest situation is the simple stain, the essence of which is to calculate the probability that a random person would match, so that you can say, wow, this suspect matches, and he says it's coincidence, but by the way, that would be a 1 in 10 to the 15 coincidence. Do you feel lucky? And an interesting point is you can guess pretty well what race somebody is from DNA. Although if you have a choice, your eyeballs are probably better. But if you just have the DNA, of course, your eyeballs don't help. Like you look at the crime scene and you can say, okay, this DNA was left by a black person, a white person, an Asian person. It doesn't help, but you can tell. And then another area that I picked up on is something called population genetics, which is very fascinating. And if you study the theory of how genes move in populations, it gives you a lot of insight into what's going on with the applied stuff. Okay. I wanted to show you, just talk to you about DNA because I think you'll enjoy hearing about it, because it's very interesting stuff. And it's very weird that in the middle of this supremely analog device of a living body, you have an actual digital component. The DNA is very digital in many of its functionalities. So here is a picture of the gene, what's called, well, this is the chromosomes in one cell. The collection of the chromosomes, or the collection of the information on the chromosomes, is called the genome. And we have 22 chromosomes that come in pairs. So there really are 2 1s, 2 2s, 2 3s. And those of you with sharp eyes can see the scheme. Number 1 chromosome is the biggest, 2 is the second biggest, and so on. So that's the secret code, except X and Y, which are special, because those are the sex chromosomes. So there are a total of 46 chromosomes, 22 times 2, plus an X, plus either a Y or another X, depending on which sex mark you check off on a form. Here's a particular chromosome. Let's look at it, and I'll talk to you about how DNA identification is done. This is the 11 chromosome, and there's a particular identification is done through a standard set of locations on the chromosomes called loci. Loci plural, locus singular. Unless you're a lawyer, in which case you use the same word for both, which annoys the hell out of me. All right, so there's one of these loci is called TH01. And I guess it's named because it happens to be near some functional gene. But it's not a functional gene. It's a bunch of junk. All of these are junk, we hope. And the designation is 11p15.5, means that it's on chromosome 11. P is the short arm. Here's the shoulders, so this is an arm and this is an arm. And 15.5 tells you something about how to find it relative to these bands, which I'm getting beyond my expertise here. It's called a tetrameric repeat. Tetra, of course, means 4. And I'll show you a picture of what I mean by repeat. So a particular person, because they have 2 number 11 chromosomes, are going to have 2 Tho1s. And theirs are going to be designated by a number called a repeat number. So they might have an 8 on one of the chromosomes, which they inherited incidentally from one of their parents, and a 10 on the other one, inherited from the other parent. You can't tell which one came from which parent. People with 8, 10, they all look the same. And a DNA profile is a collection, basically, of 13, an ordered collection of 13 unordered pairs. So there are traditionally 13 locations in United States work, moving toward 15 these days, a different collection in Europe, a special collection in Germany, because they have their own particular history that they do things a little differently. But it's fairly standard because you can buy a kit from manufacturers that lets you do this assay in a very standard way without the lab being too scientifically expert. The lab is technically expert, technologically expert. Here's a little quick lesson in genetics. This would be a father with, let's say, 2 number 11 chromosomes, in addition to all the other numbered chromosomes. And here's a mother with her 2 chromosomes. When they have a child, one of the 2 will randomly be selected. Okay, those of you that know this stuff, I admit I'm simplifying. So maybe this guy passes along his 9, his yellow one, and she passes along her green one. All the chromosomes are color-coded for ease of identification. And you end up with a child that has 1 chromosome from mother and 1 from father. So that's autosomal genetics, meaning genetics not related to sex. Okay, here's a close-up look of the part of number 11 chromosome we're interested in. Yes, it's an actual electron microphotograph, one of the few pieces of lab work that I've done. And so what you see is you have a double strand here. You know that DNA is double-stranded. So you have 2 strands, and don't confuse those with the 2 chromosomes. We have pairing on 2 levels. We have a pair of chromosomes, and within each chromosome we have a pair of strands. Between the 2 chromosomes, there can be a lot of random differences. Between the 2 strands, there are completely systematic differences. One strand is simply the mirror image of the other. So on one strand, we have TTAC, and then we have again TTAC, and then again TTAC, maybe 8 times, maybe 11 times. That's where you get the allele number for this locus. And this one, wherever you see a T, you'll see an A here. So this one is going to have AATG, AATG, and so on. Let me just explain that rule a little bit further. It's called the pairing rule. Here are the 4 bases, also known as nucleotides. Maybe there's a technical difference between these words, but I can never remember it, so go easy on me. They're called A, C, G, and T. And they fit together this way and only this way. The A and the G are big. They're called purines. They're not huge. They're maybe 300 molecular weight or 500. And the C and the T are a bit smaller. And the A hydrogen bonds with the C with a double hydrogen bond. Oh, by the way, here's a very important thing. These are called pyridamines. And you can always remember because of the common letter Y. Okay, I think that trick works in most languages. I don't know how the Japanese manage. They probably can't remember these things. So A, nobody would ever make the mistake, by nobody I mean no bunch of electrons or something, of joining an A to a T, because you just have one loose finger. And nobody would ever join an A to an A, because if you tried to, you'd have an unsightly bulge. And the unsightly bulge would immediately be repaired by some very fancy little gadget that comes along here, crimping. There's all sorts of unbelievable checking mechanisms. Big things called enzyme that are like little molecular, 1 molecule, big factories. Big fat molecules, but 1 molecule comes along and checks for errors and makes sure that there's no pairing mistakes. and other kinds of mistakes. Now, when cell divides in two, half of this thing gets ripped apart. Half of it goes to each new cell, and each part of it is a sufficient template to make the other half. Because if I rip this apart, you could know the other part is going to be an A wherever this is a T, and so on, using the pairing rule. However, mistakes do happen, especially on these monotonous strings. The mistake that happens is slippage. Let's say I'm busy replicating this thing, and then all of a sudden a slip happens. So instead of matching these four up with these four, I'm matching them up with these four. I skipped a unit or added an extra 4 base pair unit. The normal mutation prevention mechanisms in the cell do an extremely good job where it's important, but they aren't very good on these monotonous stretches that don't mean anything. I mean, you can live 100% as well with a few too many of these or a few too few. The only survival use of these is that if you didn't have variation in these, then crime would be rampant in society and we'd gradually die off, which has happened in many times in remote history. Okay, here's what the machines that do the typing actually, this is what a DNA profile looks like nowadays. When I was in San Antonio 15 years ago, I showed one of these X-rays with little caterpillar thingies in it or eyebrow thingies like you used to see on TV. They don't use those anymore. What we have now instead of caterpillar thingies is this electropherogram, it's called, which is a graph. And let's see, up here I've given you a blow-up. This is the locus D5, systematically named. That refers to chromosome number 5. And S818 is just an arbitrary catalog number. I guess that means somebody indexed it the day after 817. And I don't know what happened the day after, but you figure it out. And here is just a calibration ladder. These are the possible or at least common sizes that occur. So when we see a blip here and a blip here in a particular person, with reference to the calibration, we know that that's 11 and 12 repeats. This is all done by a version of weighing. So the person has these two sizes at the first locus. So let me give you a blow-up just in case you've accidentally sat at the back despite your eyes not being really sharp. So 11 and 12. These numbers here are an indication of the height of the peaks, which don't have much to do with identification per se, but their intensity, how many cells of DNA were deposited. And by the way, you can do this stuff, they do this routinely with 40 cells of DNA, submicroscopic. In principle, you can do it with one cell, but it's very hard to keep track of one cell. So nobody knows what you're doing for sure. But you start with something called PCR, which is an amplification process, and by using processes in a test tube which mimic the processes in the body of dividing cells, you double and then quadruple and then octuple your original chromosome until you have 1 million or 1 billion copies. I've never figured out exactly what it is. Enough to actually weigh. Wonderful stuff. Okay, now the mathematics. You have to know something called a likelihood ratio to get anywhere in forensic mathematics. This is the fundamental way to evaluate evidence. It's the ratio of the probabilities of one event under two different hypotheses. Let me give you an example of what that's based on this principle. Data. When you have data, it's evidence for one hypothesis over another to the extent that the data is more probable under one hypothesis than another. Okay, if that's a little confusing, fortunately I wrote down an example on this slide, so I don't have to think of one on the spot. Well, the next slide. So I want you to think of the hypothesis as an explanation for the event. Here's a repeat. Okay, here's the event. The dog is barking. Two explanations. There's a stranger about, or the dog is hungry. Okay. The dog, and I'm saying, and my idea is that the barking is evidence for one of these explanations rather than the other, providing you believe that the dog really barks a lot at strangers, but not with the same probability when it's hungry. So my assumption, just take my word for this, dogs bark 84% of the time when there's a stranger, and 7% of the time when they're hungry. This is averaged over my own dog. Okay. So therefore, the probability of barking when there's a stranger is 87%, which is hugely more of the probability of barking when it's hungry. In fact, the ratio, if you work it out, is 12. You could say barking is 12 times more characteristic of stranger than of hungry. So it's evidence that the dog is being mean rather than needy. It doesn't mean it's not proof. The rarer things happen. So here is the statement again. Now I'm looking at DNA. A typical situation, a simple situation in a crime scene would be that you have DNA and the suspect matches the DNA. So if the suspect contributed, that's sort of normal that they would be the same. But if the suspect is just a random person like he says, there's an amazing coincidence. So if we do a likelihood ratio, we would have some huge number. And I'm going to try to hurry up to get to some stories now. If the DNA profile at the crime scene is something that occurs in 1% of random people, which would mean that you're only seeing a fraction of the genome. I told you before 10 to the 15th, now I'm telling you 1%. Who is this guy? Does he just change the numbers? Yeah, I just changed the numbers. So this is a likelihood ratio of 100 supporting the guy being the donor. Okay, the prosecutor says, damn it, I want, the jury wants 10 to the 15. I say, well, I'm giving you 100, and that's better than you're getting out of a cop testifying. Where the jury's question is, what's the probability the cop would say that if it's true, divided by the chance he would say it if it's not true? The cop's testimony isn't worth 100. It's worth 40. So you don't compare the 100 to the 10 trillion you might get. You just evaluate it on its own merits. It's really good evidence. Okay, here's how you actually use it. Let's suppose we have some hypothesis, such as suspect left the DNA, suspect killed the girl, and we have some prior belief. In other words, we think it's one chance in 1,000 or 10,000 that that's true, prior to hearing the DNA. Why? Because the suspect has given a hugely good defense in terms of alibis and really upstanding person who hasn't committed so many murders in the past. And then we have this DNA, and we have a likelihood ratio, which we represent as an arrow. And the length of the arrow, actually it's just, each tick mark is a factor of 10. So we take the log of the likelihood and measure it off here. That's how you do it. And that means the likelihood, then you get to a posterior probability. So if you're a logical person, which means you can follow a simple thing like the derivation of Bayes' theorem, then if you had this belief originally and you're the DNA, you should now have this belief. Let me emphasize that. Let's suppose that I have a prior belief here, having heard a set of facts different than what you've heard, or making a different assessment of them. Like I'm differently swayed by the testimony so far. So we have different prior probabilities. We hear the same DNA evidence, meaning the same scientific arrow. It's not subjective how long the arrow is. So we have the same likelihood ratio. Well, we end with different posterior probabilities. So the point is that evidence tells you how to update your belief. It doesn't tell you what to believe. Now, what are the fingerprint people doing? They're contradicting this. They're telling you, in effect, they're telling you that my fingerprint arrow is infinitely long. So I don't care where the tail end is. It can be way over there in Jutland. Nonetheless, the head is going to be in Sweden. Now, if we want to, we can think of the DNA evidence as being a different arrow for each chromosome, for example. And they just string up one arrow after another because they're independent and it really comes down to multiplying probabilities. So typically we have some prior belief. We have maybe some threshold of determination. It's the jury's job in a criminal trial, but in other cases it may be the scientist's job. And if our arrows Get us far enough, we make a decision. In a crime situation, yeah, we might be in this situation, in which case it's tempting to say, well, for any reasonable, credible beginning point, no matter how far to the left I put it, this arrow is so long that it's going to get over here. It's a tempting way to believe, but you get yourself in trouble. There's a slippery slope if you start believing that way. Let's see. I think I can skip past paternity. Then I wrote this kinship program just to see if I could do it, originally about 93, to generalize the paternity question. So, for example, let's suppose we have two bodies which we think may be the child of Mr. F, or living reference, or they may be unrelated. So the kinship program can calculate the likelihood ratio for any problem of this sort, not just the paternity problem. And I thought, well, it would be a nice giveaway just so people can get used to the quality of my work. Before I knew it, it was the centerpiece of my work, what I'm best known for. Started out by being very heavily used in Copenhagen on immigration work. And I guess, I don't know if it's good that I didn't go give it away. But if you're not into the free software model, it's good. At some point I decided to go into crime. I think it was the girls. And let's see. A little digression here. Just so you remember that the whole world isn't APL or DNA. And I really like this picture from last week. Usually my slide talks have applaud and laugh interspersed from slide to slide. But I hope you appreciate that today I'm trying to do it without nets. So you have to guess when to applaud and so on. The calculations for simple crime stain matching are very easy. If you have the same allele at both chromosomes of a locus, then the question centers on the rareness of that allele. We have population data to say some alleles are rarer than others. And the chance of a random person having this particular configuration would be determined by the formula Q squared. Maybe 1 over 25 would be a typical value of that calculation. When there's two different types, it turns out there's a factor of 2. And so more typically you get a number like 1 over 12. So it's by multiplying together 13 or so numbers of this order that I end up with a probability of 10 to the minus 13 or 15 for two random people to match. Trillion, I'm claiming. Let's be consistent. Here is a little graph, a histogram of typical allele frequencies, 5%, 10%, 15%, 20%. I'm not going to do that, actually. Here is variation among races. So here's the allele 8, 9, 10, 11, 12. Sorry, the colors aren't too well chosen. So you can see that the 8 allele, while it's 10% in Caucasians, and these two center bars are different black populations. It's quite unusual in blacks, and it's 25% among Japanese. So that means if you have a crime scene stain, and you see an 8, that's evidence that the person who left it is Japanese, because it's a more typical result from Japanese than from the other races. It's actually, if you think about it, exactly an example of a likelihood ratio that I told you about before. Now, if you look at a particular profile at the crime scene, this isn't huge evidence, but I've got 26 alleles, 13 loci times 2. So I've got 26 little pieces of evidence, some of which give me a factor of 2, some more, some less. And using that method, looking at all 26 of them and multiplying together the ratios, I can get actually a huge likelihood ratio supporting one race rather than another. And on the average, this is what I get. This is sort of my invention doing. Well, I didn't think of it, but I'm the first person that made it work. So the average distance between African Americans, for example, and this cluster of Asians is quite a large number, 300. Well, 300 is large in what sense? Maybe I should draw a better picture. The point is, a better picture would show that the African American point is really some big fuzzy ball. How fuzzy? Well, maybe the fuzziness goes this far, but very little of the fuzziness gets this far. Very little. So your chance of confusing an Asian and an African American is extremely small. On the other hand, as everybody knows, it's really hard to tell Koreans, Chinese, and Japanese from one another by looks. You can tell from the way they act together and from the way they dress, but you cannot tell purely from their phenotypes. At least the Japanese tell me they can't. I can. So here's some specific. Now with horses, it's even easier because people purebreed the horses. So I don't know what that means. The discs are less fuzzy or something. Anyway, here's some Italian abbreviations for horse breeds. And you can see the numbers are huge, distinguishing one breed of... well, in this case, it's one horse. So this horse was a ringer. This horse was being raced in non-thoroughbred races, and it was suspected of being a thoroughbred. So this analysis was part of a little detective story. I never could figure out what happened. Of course, the case was in Italy where... I don't know how to... Never mind. Let's see. Here's how I run my business. I install the program at different labs, and they can use it as long as they want, as long as they don't give it away or something nasty like that. But if I do my job well, they'll pay me an annual maintenance contract. And in the long run, that should make me rich beyond the dreams of Midas and Croesus. And if I can keep them happy. Some of them will be more happy if I can give them a Windows product. So that's why I'm here, so that all you can help me create a Windows product, because as I may let you see, the product at current is not Windows. All right, we have time to go through one or two stories, so let's see how it works. I decided to move this one to the top of the list. And for any of you who happen to read the abstract, you might notice that that's not operable. Okay, I thought it was very intriguing that DNA lets you do this. You can peer, if you're a nosy type of person, you can peer into people's bedroom windows. And in this case, in a remarkable way. What happened was a man and a woman were badly injured in an automobile accident. They were taken to the hospital and treated. They were burned. And for reasons that nobody ever will understand, at least I won't, after they left the hospital, they committed suicide. It just makes it spooky. I don't know what it means. Now, F was positively identified by DNA comparison with his family. He had a wife and children. And the police enlisted the help of a local DNA laboratory and did that. Then that leaves the question, who is G? And it wasn't hard to learn that she was the sister of F, because as soon as you get back to the family, you know, they can sort of take a little census and get on the phone and see who's missing. You've probably done this with your families. However, the examination should have stopped there, but nosy people will never stop nosing. And some things were discovered that maybe shouldn't have been. So here's a little diagram for the first question. What's the connection between F and G? One hypothesis is that they're siblings, same mother, same father. And the other hypothesis is that she's unrelated. So with my kinship program, we could make a little calculation, or you could just look at all the alleles, the chart of genotype of genetic types, and to put it qualitatively, they share genetic traits in 18 of 20 tested systems, which would be quite normal for siblings and a remarkable coincidence for unrelated people. So qualitatively speaking, that's huge evidence that they're siblings. The explanation for this, the DNA, is 300 some odd times better explained by this picture than this one. So we carelessly assumed that this one must be true. Why is that careless? Because all my evidence really says is that this one is false. That's different. Took me years to catch on to that point. As my old violin teacher said, I said, that piece is so hard to play. He said, I know, I am 86. So anyway, this was a big family. And they had 6 children. So we got a hold of all 6. This is the we of pretended participation. And every pair looked like siblings. More like siblings than half-sibs, much more like siblings than unrelated. But they aren't. You know why? Let's look at 3 of them together. These particular 3, F, A, and C. Let's look in particular at the locus VWA. VWA was a famous Swedish doctor, von Willebrand. The type with one child was 1417, the next was 1416, the next was 1418. Now, all genetic testers know that if 5 alleles are represented among the children, you can't have just 2 parents, because 2 parents have between them only 4 alleles to contribute in a system. This isn't that pattern. This is only 4. So I can always trick the genetics people when I show them this. You just can't arrange it from 2 parents. So there must be at least 3 parents. All right, let me prove that for you because I'm a mathematician, so I deal in proof. Here's the 3 children and their types. Now, there are 3 14s among the children. So let's assume that there are only 2. There's a little background. Let's assume there's only 2 parents. So one of the parents must have contributed at least 2 of the 14s. Maybe all 3, but at least 2. Let's say the mother. Let's draw some arrows, okay? So the mother contributed the 2 14s. That means that this 16 and this 17 came from the biological father. Okay? So that tells us that this guy, the biological father, it tells us that he has 16 and 17, but that fills him up. He can only have 2 alleles. He's only got 2 chromosomes in that pair. So that means he cannot be the father of a 1418 person. We need another parent to explain this. Undoubtedly another father, because everybody knows who their mother is. It's a wise child who knows his own father. Is that a famous saying? I mean, I think it is a famous saying. So when I first looked at this some years ago, by hand, I worked this way and that way, and I found a way of arranging the children that was consistent. 2 fathers, 1 mother. It was a little weird the way the children's ages fell into this picture. I'd like you to think about this woman's life. I'd like you to think about the fact that she comes from a country that's maybe moderately conservative, at least externally so. And she started with husband number 1, and she had a child 75 years ago. And then she jumped across the street. And then she's had a little argument with this guy, and she came back to the first guy. And again. And then she remembered how exciting this guy was. And so she had this child. And then she went back to this guy. It's what you would say a low prior probability. Now, after a few years, I'd spiffed up the Kinship program. It's a part of the program that I use very often my own self because I do a fair amount of consulting or fooling around or whatever. And the parts of the program that I use are really convenient to use because I hate extra keystrokes. And I like things to be easy. So eventually, I discovered with my newer program, it wasn't so hard to try all the combinations and discover there was a second combination that was also consistent with all the observed DNA. Whew, look at that. Like the way those numbers line up? She had spouse number 1 with 2 children, and then she moved on to spouse number 2. The only mysterious thing is that the official records say 1 father for all the children. If I tell you what the country is, you can't tell anybody. You can't leave the room. That's not a country. It's a city in some country. When I wrote this up for proceedings, I talked to my colleague in Sapporo and asked him, about putting his name on the paper. He said, no, don't put my name on the paper. He said, the point being that these people were never told these discoveries. So this picture explains the data 40 million times better than this one. All right, that means that this one, we can, practically speaking, we can forget about this picture. Doesn't mean this one's correct. Maybe I can find something better still. You know me. All right, let's see what my next slide says. Remember this, they all look more like full siblings not only than unrelated, actually I should say than like half siblings. Here's the idea. If the fathers are brothers, then they would be what we might call three-quarter siblings. It's not a standard term, but I'm planning to introduce it in the next edition of Forensic Mathematics. So that means, here's our original picture, here's our still better explanation. Okay? And I do the likelihoods, and the DNA explains this picture 7 times better than the other one. Now 7 times, that's not a huge likelihood ratio. As a matter of fact, if you think about the relative priors, when a woman has 6 children from 2 different fathers, just I tell you that, never mind the DNA, what's the chance that the fathers were brothers compared to they're not? Would you say it's at least 1/7 that the fathers are brothers? I suppose not. So I suppose the prior maybe drowns out the DNA here, and notwithstanding this 7 factor, you might still believe, okay, this second picture is kind of unlikely. But I believed it. And the reason I believed it was that when I did this same analysis with the wrong rearrangement of children, the factor was, I think, bigger, much bigger. Anyway, so luckily, for the wrong reason, I believed this. For whatever reason, the laboratory in the Sapporo, in the unnamed country, did further genetic testing. They tested the Y chromosomes on the males. Y chromosomal testing is generally limited to males due to the fact that women don't have a Y chromosome. So it would just cost you money and you would get nothing. By luck, we have, according to this picture, as well as according to the other one, 1 male in each cohort. Each father. So these males have the same Y chromosome. That means that their fathers have the same Y chromosome. That means either it's an enormous coincidence or somewhere back in history their patrilineal lines converge. They have a common grandfather or great-grandfather along the paternal line or something. So that was enormous confirmation of this picture here. In other words, my number of 7 is now going up to 7,000. Okay, so depending on the time, that was my first possible stopping point. And let's see, according to when I started, there's 11 minutes for an hour. According to when lunch is, there's 6 minutes. Either way, we have some time, and I have a question. Do you have any questions? Yes, sir.
In your experience, I guess testifying, have you found any court where reasonable doubt has been defined because of probability?
Oh, no.
The judge instructed, well, you could be wrong, why don't you send that?
No, this is just a mathematical model of what's going on in court. In reality, there is a psychological literature, studies, which suggest that the way the jurors actually interpret likelihood ratios like this may in some cases be like this. What defense attorneys love doing is, let's say the likelihood ratio is 1 million. So basically this means that you should be 1,000,000 times more sure that this guy is the culprit than before you heard the evidence. So if the prosecutor made any kind of case at all, this should slam the door, hang him high, in my view, if you believe in hanging at all, that is. So hypothetically. I don't, but rhetorically speaking. However, the defense likes to say, well, so what you're saying in effect is that there are 7 men in Los Angeles, or 7 people who share this, who could equally be the donor of this DNA. And he's trying to plant the seed that makes it about 14% that my guy did it. And prosecutors don't understand their way around this one particularly well either. And I'm sure it works from time to time. The catch is, one way of putting the catch is this. Well, the way I like to, just in general as a pedagogic point, when somebody says something that shows they misunderstand, instead of just contradicting them, I like to see their reasoning and say, oh yeah, you're thinking as if the truth were such and such. Your idea would work if in fact all 7 million people in Los Angeles had an equal chance to be at that crime scene on that day. So if you have video cameras showing all 7 million of them going in, then I support that argument absolutely. Let's see, one thing that I mentioned in the well, I'll talk about one idea, maybe not much in the way of slides. One area I've been working on in the past couple of years, sort of a variation of the mass victim identification problem. The mass victim identification problem, by the way, is this. You have a big pile of bodies. The canonical example would be an airplane crash. So you have 228 more or less mutilated bodies. And you have a similar number of families who have generously given their DNA to help you identify. So you're going to compare the families with the bodies, and you're not going to see numbers like 10 to the 15, because it's only a relationship. It's not exactly the same DNA. In fact, so you have 200 times 240,000 comparisons. And that means that for any given person, for example, among the bodies, let's say you're looking for daddies. There's going to be one real daddy, right? And a few hundred other men who are not the daddy. And there's about a chance in 5 that one of those non-daddies would look like a daddy. So that means out of your whole tens of thousands of comparisons, you're going to see a huge number of spurious relationships. So you need some strategies and some subtlety. First, to do a screening between the one list and the other, and secondly, to sort out which of the tentative IDs are legitimate. So I first learned this idea in a very nice model example, an airplane crash just like I described. Then it came up with the World Trade Center identification, where the piles were a little bit bigger, and there were more subtleties, like very badly degraded DNA. In the airplane crash, the bodies were conveniently lying at the bottom of the ocean off Nova Scotia, where the DNA is very well preserved. Ideal for a beginner disaster. Then you have the case, something very analogous, similar, same software should work. Offender databases. Every civilized country, except Italy, has a national DNA database. And in the national DNA database, you put the DNA profiles of pretty much everybody who commits a crime or runs into the police. You collect their DNA, put it into the database. Then if subsequently you have a crime and you can collect DNA at the crime, which is hugely often, now that you need only a handful of cells, house burglars normally leave DNA, you just look it up in the database and you go knock on the door and say, you're under arrest. It's very economical. So that's why every country, except Italy, which loves individual liberty more than the rest of us, or is influenced by corruption, has bought into this. However, there are organizations such as the ACLU, which I support every year, that takes issue with this and is concerned that in some way this will infringe on individual liberties. So just to play with them, I said, well, let's do this. Let's go a step beyond. And sometimes we'll find a DNA profile at the crime scene that we do not locate in the database. I'm not the first one to get this idea by any means. But nonetheless, there are people in the database who resemble it. And so, particularly in the UK, they followed this idea rather aggressively. If there's some commonalities between the crime scene and some of the people in the database, and that they're so energetic, they'd make a list of 1,000 people out of the 5 million database as potential suspects. And they'd follow 1,000 leads. And 10% of the time they'd catch somebody. And then they'd claim that at $2 million per investigation, it's still a bargain. Maybe it's true. Let's say it's true. I've got a slightly different view, which is, first of all, that they're doing the wrong mathematics for searching. They shouldn't have 1,000 leads. They should have 1 or 10. And secondly, that we should mass produce this. Instead of breaking our necks trying to solve this case and then this one and this one, let's toss 100 cases into the hopper, see which ones have a huge similarity to one of the offenders, and just start at the top of the list, priority order. Do the easy ones first. Job satisfaction. At the end of every day, you solve a case, you take it home. So that's what I'm working on. And let me see if I have a few results just to run through for you based on pilot projects. So here's a really nice story about a famous case, a one-off case that was solved 6 or 8 years ago, having to do with some vicious stuff in Wales and some malfeasance where the police and the prosecutors conspired to convict the wrong people. So there was an enormous public outcry when they were exonerated, when DNA got better and you could exonerate them. And in order to redeem their reputation, they pulled out all the stops to search the database, and they actually found an uncle of a 14-year-old boy in the database who tried to kill himself when he was being arrested. And in my book, that's as much a confession as when O.J. tried to do it. Of course, it depends on having a relative in the database. So we did some research and we figure, well, a lot of people have a relative in the database. How many of you have a criminal relative in the DNA database? Okay, let me suppose I just limit that question to those of you who are convicted felons. All right, 30%, about what I thought. So the idea is that you look at the profiles, and they just look for this matching pattern. You see sharing alleles, but that's totally stupid because here's a graph again of common alleles being the big circles and rare alleles being little circles. Sharing little circles, that's what counts. But the British, bless their hearts, never noticed that some circles were bigger than others. I mean, they knew it in other ways, but they didn't think you needed to take it into account here. So here is the crime scene in the middle. There's a guy on the left who shares some circles, but not very incriminating circles. Here's a guy on the right who shares some incriminating circles. So we go knock on his door and say, listen, do you have any relatives that you'd like to rat out? And the British detectives, by the way, are very good. And when they ask that question, it's much more persuasive and availing than when I ask it. So let's skip along. So what we did this with our pilot project. I think we had about 100 cases that we put in against a few hundred unknowns. And so out popped a suspect. We had a likelihood ratio of 300,000 or so for brothers versus unrelated, and based on harebrained estimates, if you will, of what the prior probabilities are, I still thought this was in the high 90% to be the true guy. And I think what happened was that as soon as we saw this on the computer, I was in the DNA lab in this particular jurisdiction, So the head of the lab says, okay, he says, go look up this case. So she leaves the room, 10 minutes later comes back. Okay, that one's actually been solved and right. We have the right guy. We didn't solve a new case, but we solved a real case. Not a simulated case. Maybe it's a simulated solving of the case. Then a few minutes later, we get another hit. This one again was solved. Then there was a third case, and this one was unsolved. I think we became confident that it's right, but they couldn't prosecute it. The problem was this, that the evidence at the crime scene was a cell phone. You can't believe the things that people leave at crime scenes. Unless I tell you that they're stupid. But there are a lot of people that go into a house, they commit crimes, they have a ham sandwich, they defecate on the floor, they leave their cigarettes. They leave a big sign basically that says, here's my DNA, arrest me. And so they left the cell phone. The cell phone had the trace DNA, which was matched to a relative in the database. But unfortunately, the cell phone had other people's DNA on it. And there's no particular way to say which person that had DNA on the cell phone was the last one to handle it. So the prosecutor didn't go for that one. So that was the first pilot study. We've done a follow-up, and the results look very good, but I don't have a report on them at this time. So let me leave it there, especially for those of you that are hungry. It's time to go to lunch. Thank you.